audible. So let's get started. Today we are going to discuss a little bit on the physical sides of things and the logical side of things in terms of the database. So I have a few slides with me, so not many this time. So let's try to put some attention or focus on how we basically understands the structures in the database. So with this, okay. We take the pointer as usual. Okay. So we go to this first screen here. So I'm not going to discuss too much about the instance because we last time discussed many things about the instance. We also discussed about how the background processes work. Right? So this diagram is actually a subset of or like it's a very high level picture of the instance as well. And then also what is important for us is the physical side of things here. And you can see that background processes like the archive process, the log writer process, checkpoint process, and the database writer process, they're all basically writing or reading data from these physical files. So Oracle database comprises of all these physical files as well. So let me just give you a small briefing about these files as well. So when you retrieve data, when you store data, as in just data, that will be stored inside these data files physically. Okay. And when you are doing changes, you need to make sure, or Oracle needs to make sure that it tracks the changes that are occurring at a transactional level, at the user level, whatever the changes that you do. So it records these changes. It's a very lightweight mechanism that they use in order to track these changes, and these changes are recorded in the redo log files. At the same time, in order to maintain the integrity of the database, Oracle internally use a set of files, and they are called control files. So you could see that all these files have what you call have multiples of them. So redo logs, if you take, they are you can see that this particular file has another copy of it. So we call them members. Control file also, we call them multiplexing of control files and the redo log files. In a sense that what we are trying to do is we are trying to keep copies of the same file. So in the event if one file is damaged, you still can recover from, or we can survive sometimes with the use of the second file or the other copy. So likewise, you have that flexibility of adding multiple copies of the same file. So you may have to understand that since we are doing IO operations, the moment you have multiple files, Oracle has to write to all these files together. So in parallel, right? So there will be some effect on the IO performance as well when you try to increase the copies at a very larger level. But generally speaking, having an extra copy of the same file would not make a big impact on the performance. We also have something called as archive files, which we store separately. So archive files are basically backups of the redo log files. So you can see here, archive process takes backups of the redo log files and store them separately in order to support what we call recovery. So we will not talk too much about the recoveries here because we will probably talk about it sometime later. This is basically some of the files that you find in terms of the database. So this database is actually a collection of all these files. So in essence, database is logical because it's a combination of multiple files. Okay, so it's not just a single file. So in terms of the physical architecture or structures within the database, the files or the data is actually getting stored in a persistent storage. When I say persistent storage, those are physical files, right? So you make sure upon a restart of a machine, the file that content is not going to get erased, right? So if you put it in on a volatile memory or your physical memory might get disappear, right? So here we store them in persistent storage to make sure that it retains upon a machine restart as well. Starting with 21C onwards, so here we are talking on, currently we're talking about 26 version, right? Or 26 AI precisely. So in these types of, starting from 21C onwards, Oracle do not support non-CDB databases. They only support CDB databases. So CDB, B stands for databases anyways. So CD basically stands for container, right? So container databases are supported only, is the only choice that you have from 21C onwards. So we have not yet discussed into depth about what a container database is, but this is just for your information purpose. We previously had non-CDB or non-container databases in previous versions. Even in 19C, we have both CDB and non-CDB option. But starting with 21C, you are only allowed to have container databases. So a container database might carry multiples of pluggable databases. So we will take a look at the PDBs sometime in one of the upcoming sessions. Okay. Now, since we are talking about physical structures, how Oracle store data. So we can choose different locations to have the data files stored. One would be the OS file systems, right? Generally speaking, if you take OS file systems will be formatted, right? So it could be a single disk, but it could be also a bunch of disks. So when you are having a bunch of disks, you may not get a disk as is. So what the storage administrators, what they do is they basically combine all these storage or these disks together and create something logical out of it. So the content will be spread across all the available disks in the disk subsystem. So this, these small partitions or whatever you call it, we call, sometimes we call them as logical unit numbers also, or LUN or LUN. So they are basically created as a logical, storage for us. But under the sea, those content will be spread across multiple disks, right? So that is for performance, availability. That is how they are being presented. So logical volume managers we use in order to make that transparency. So Oracle will see them as disks, but they're just logical because it's a combination of it's a mix spaces coming from many disks under the covers. Okay, and then you also have something called as clustered file systems. So when it comes to clustered file systems, it gives that the additional feature of a concurrent access. So when somebody is modifying a file, at the same time, another person will be able to modify the same file. So just imagine a situation like you have, let's say you have a Google Sheet that you're updating. So many people can share, you can let it be shared by many people and do concurrent modifications to the same file. It's not just like you open your Word document now and then let somebody access it, right? So, and do multiple changes at the same time. So if it is a cluster file system, if you can host your database and multiple machines who has access to the database will be able to fetch the same content and modify at the same time. Okay, so that's basically the idea behind cluster file systems. And then we also have something which you might have not heard of. This is called Oracle Persistent Memory or PMEM file store. So with PMEM file store, what we try to do is we when it comes to disk subsystems or disks, right, in general, when you have access, when you try to access data from disks, it is kind of or relatively slower than that of accessing from memory. So that is why we discussed probably in the previous sessions that the Oracle instance is maintained, or SGA is maintained in memory, so that you can cache it and you can retrieve it on demand, which is faster access, or which provides faster access over uh, physical disks, right? A similar situation here, but here we are trying to store persistent content, right, in memory. So this is not within DRAM. So as you know, DRAM is volatile, and whatever you store there might get destroyed, maybe due to a power failure. But here we use um, something called as PMEM, right? So this is persistent memory that we are making use of. So this is non-volatile memory. So we make use of non-volatile memory, and you can create file systems on top of it using ext4, and it has to be mounted using a specific, or special format, which we call fstax, right? So if you do that, then you can present this to Oracle database. And mind you, you have to start your database instance in order to mount this file system also, because it is very specific or special to Oracle, right? Not other components or software be able to see this. So there are certain prerequisites as well, such as, I mean, I think this is something provided through Intel. So you need to have an Intel motherboard to support this. So there are certain restrictions as well. But the good thing why we have PMEM file stores is basically for performance. So when you read data, this time from a PMEM file store, you're reading from memory. So it's a persistent memory, unlike DRAM. But as I said before, it's going to be a memory to memory transfer. Now, if you access them from memory and put them into the SGA, that is going to be a memory to memory copy, right? It's not a storage access that you're going to perform, which is going to be slower than a memory to memory copy. Okay, so for that advantage, we can even opt for PMEM file stores. But for PMEM file stores, there are certain conditions. Although you are okay to store other types of files, Oracle basically recommends you to use PMEM file stores for data files and control files only. Right? And this is supported only for single instance database, because it is not supporting a clustered environment. Okay? So that is why we have to use PMEM for single instance databases. And of course, I think probably in the second day of our series, we discussed about ASM and how ASM behaves. So ASM is also another option that we can consider when we are storing our database files. Okay. So this is basically about the physical structures where you have the option of storing your files that is part of your database. Okay, then we also have something called as OMF and user managed files. So why this slide is blank is mainly because I wanted to show you what exactly this OMF and user managed files is, right? So let me just quickly stop sharing and take my let me just take that. Okay, so this is my database. So I have this is the container database that I have. I have one pluggable database available, and currently in my container a root, right? So here it will give me the name as root. So under root will be my first container, and so root is more or less the managing entity, and then I can start creating many pluggable databases in my CDP or container database. So this basically, or PDB1 basically carries our user data, but then root also is another environment, maybe for administrative purposes you can use. Okay. So what I'm going to show you is just fetching data from the root container. Let's check select name from the data file. So you can see that most of these, okay, so you have the data files, right? I showed you data files as one of the key figures or key physical structures in the database. And you can see that the file has a name, right? And it also have what we call an incarnation number here. Right? So it's a long, it's a with a lot, many number of digits. So why these incarnation numbers have been placed here? Now, when you are spinning up or when you are creating or when you're adding a data file, right, you will be basically making use of what we call a table space. So table space is something logical. We will discuss it later on. But here what you are seeing is that the data files which are part of the table spaces. Now, when you see these extensions or these numbers, these are created automatically by the system. Okay. I'll show you one example. One parameter here. So show parameter create. So I have this entry in my parameter file called db create file list, which determines where I should be creating my data files. All right. So the idea here is that this is ASM disk group, which we have studied earlier. So when I want to introduce a new data file to my environment to this database, I don't need to say where the file should go. I don't need to tell database, I have a name or this is my name. So that is not really required. Why? Because when you are dealing with the database, we don't really go into the physical layer of the database and, talk about what is my data file and how many data files I have. I mean, for managerial purposes, we might still use it. But for users, well, users, it may not be really really important. Okay. So when you have this parameter set, right, then we are enabling what we call Oracle Managed Files, OMF. You can see here. Okay. So you can see that we have Oracle Managed Files. So what's the impact of it? So when it is Oracle Managed Files, we can enable it through this parameter for the database files. Okay. And we also have entries for the redo files as well. Right. So I have not set a value here, but for data files, I have set a value here. So when I add a new data file, I don't need to give a name. I don't need to give a path because that is all automatically taken from this parameter. Right. So for your reference, this big name that you're seeing here is actually an identifier for my pluggable databases. Right. So when I have pluggable databases, I will be having this big code number, right, which is actually an identification for the pluggable database. So you don't need to worry too much about it. So this structure is automatically identified and the database files will be kept here. So while it is easy for me to create or add data files or create table spaces, because when you're creating a table space, it is compulsory for you to define your data file or data files. So when you do that, you don't need to mention the name, right? So that's one of the advantages, and the path as well, because it's already set. And the other thing is that when you are doing modification, let's say, for example, I want to maybe get rid of a table space which is not being used. So you might just do what you call a drop command against the table space. So the data files which are part of the data table space will get dropped automatically as well. So addition, removal. So all that is easy when you let Oracle to manage these files. So how they are going to name it is not really relevant for us. Right? So they may have an internal reference for this, and that doesn't really matter to us. Because when you are dealing with data, we don't really go into the data file level. But maybe we are considering our table spaces, we might consider our tables, indexes, and so on. So that's why I said it's easy if you have OMF enabled. But does that mean that we don't have that option of going with the user managed files as well? I mean, if you really want, you can do that as well. So let me just show you one thing. Okay, so let me just say select table table space in from DBA table spaces. So I have some table spaces here. We'll talk about it a bit later about the table spaces itself. But then I have one called users. So let's check select file name from DBA table spaces, where table space name equals, we take users. So I have a table space called users, which has okay, so the problem here is it's not able table spaces, DBA data files. Okay, so you can see that this is that data file, which is part of the users table space. So if you go up ending with 857, you will be able to see that here. Okay, that's this one, right? So it's that data file. So you can see that it's a file that is being created by Oracle on the OMF, right? Now, if I want, let's do this alter database, alter table space, users, add data file, and I'll give a path, U01, maybe soft. I have this path actually in my machine, software, say users02.dbf. Let's give it a size 5 megabytes or maybe 10 megabytes. Okay, so as you can see here, this time I have given a manual entry, right? So I've given a path, I've given a name to the file, and I have also given a size. So size is, of course, you can let it grow, right? So that is something that we can do separately, but here I have given a manual entry. Check the files now for this table space. You find that there are two files as expected. One is the OMF generated file, right? The second one is the manual file that we have generated. So the moment if I just do a command to drop this table space users, mind you, this file will not get dropped unless we explicitly ask the data files to be dropped. But without saying any additional clause, if you just say drop the table space, this file will be automatically dropped because that is being managed automatically by Oracle. Okay, so you can easily see that OMF is something which is easy for us to make use of. I mean, if you have that, then it's easy for us to manage. But then user managed files is also an option that you have, but it is more conventional, more legacy, right? So if you are new to Oracle, I mean, you don't need to really worry about this part, right? You don't need to remember this syntax, right? As long as you have an entry in the DB create file dest, it's just a matter of adding a file with something like this. Let me just do that as well for you. Can we just say alter table space users, say add data file size 10. Simple as that. So the moment you do that, let's figure out the files that you have. I'm sorry. We are expecting 3 files now under the same table space. You can see the third file as well, but this time it has that incarnation number as well, right? So this is managed automatically by Oracle. So we don't need to worry about the rest of the syntaxes. So that's the beauty of using Oracle managed files. Okay. So hope that part is clear. All right. So we go into the next section of logical structures. So when it comes to logical structures, it's important for us to understand this particular component. So take the point out. Okay. So we just show.
Mr. Ben,
Yeah.
you haven't shared the PowerPoint presentation.
I'm sorry. Sure. Thank you. Stop sharing and share it back. Thank you for letting me know. So we come to these logical structures. So as I was saying before, it is important to understand this particular concept. Okay. Uh, uh, I mean, these are real fundamentals that you need to understand. So we talk about the logical section here. You take table space. We earlier observed the data files. So we had this table space called users, if you can recall, which initially had just a single file, right? So table space can have one file, one physical file, but we added two more, right? So table space can have one file or can have multiple files attached to that. But that file cannot be cannot be part of another table space. It's not possible. Okay, right. Then, okay, so here you can see one table space. Let it be users, the one that we just saw. Users table space now have three. I mean, it has three data files, right? So just assume that we have only two. So this is one data file and this is another data file. And you can see that this we are storing tables here. We have indexes, right? Okay, so there are tables that resides in the same data file of the same table space, but there are some tables that spreads across multiple data files as well. Now, tables, indexes consume space in the data file, right? Because when it comes to data, data has to be stored inside tables. If you have indexes created on that, the moment you add more records to the table, the index will also grow. So that means index will also consume space from the physical data file. So the components or these objects that take space from your physical space is what you call as segments, right? So table is a segment or is an example of a segment, index as well. So if you take one table space, as you can see here, right, in this section, you can have multiple segments stored. So you can see how logical, table space as a logical entity. Why? Because it comprises of one or more data files. So this is the container, right? So this entire container is your table space. Now, our example, users table space had three data files, right? So this is the container, and that is what we call a table space. So it's completely logical, right? So this logical table space can have multiples of segments. What is important in one of these situations, we saw a table segment getting spread across multiple data files. How is it possible? Okay. Now, when you are defining a segment like a table, when you're creating that, obviously you need to have space. Sometimes you may not need to have space at the beginning. Why? Because you may not really require to enter data. You may not have data at all in the first place. All right. So, which means space allocation, we can differ. We call it deferred segment space allocation, right? So we can defer the requirement of allocating space for this segment. I mean, let's take an example, this table. Why? Because initially we may not have data, but when you are entering data for the first time, you need to allocate space for it. So once you allocate space, it will keep growing, right? So how would Oracle allocate space for this table or maybe the index to grow? That will be done by way of extends, right? So the segment will go by extents. So how many extents you want to have? Maybe initially you need to have just one extent. Okay. Now, what is the definition of extent then? Extent is actually a collection of multiple database blocks. All right. I hope I think if I'm not mistaken, I explained you about a database block. So database block at a logical level is the smallest IO element in the database. But when you are fetching your Oracle database block, take an example. Generally, our database block size is 8K. You can have a standard block size defined at the time of database creation. So this standard block size you cannot change unless you recreate the database. True enough, there are non-standard block sizes that you can define in your environment. That's a different story. But when you take a standard block size, that cannot be changed after the database is created. Now, let's say maybe you pick 8K block sizes, right? So what happens is that when you're fetching your data, let's say from your disk to your SGA, the one that we spoke about last time, you need to see how many OS blocks you use. Because as an example, your OS block size might be just 1K in size. So in order to retrieve a single Oracle data block, you need to have 8 operating system blocks read. That is at a physical layer. But for you, it's a logical Oracle block, right? So what do you have in the block? Block carries records of a table, right? Or blocks may carry index entries. Because we talked about the segments, right? We identified table as a segment, as an example of a segment. So segment should have data, right? So data will be actually stored in blocks. Now, coming back to the extent, when you are allocating extent, you can either define a size for the extent, or you can let Oracle to decide the size of an extent. Okay. So you can define the minimum number of extents you want to have, maximum number of extents that you can have, right? All these things as attributes you can pass onto your table, right? Or it can also be specified at the table space level. So if you specify something at the table space level, by default, all those attributes will be derived or inherited by the table, the segments that you create within that. But you can even override at the table level or maybe index level, or when you're creating a segment. So it will override the settings of the table space also. That is also possible. Okay. So talking about the extent, let's take an example. Extent size 1 MB. So if I have defined the extent size of 1 MB, it is clear, right, that it is way bigger than the Oracle block, right? Block size was 8K, right? That's what we discussed. So what happens is that when you're allocating an extent, it ultimately allocate one or more database blocks. So if your extent size is 1 MB, that is 1024 kilobytes, right? So you divide that 1024 kilobytes by 8, and then you can arrive at the number of blocks that you would be allocating initially within that extent. Okay, so what you have to understand is that the segments in general will grow by extents, right? An extent can have just a single block. So your extent size is equal to database blocks, then it will be just one block. But typically, extent sizes are much bigger. So an extent will carry, therefore, multiples of database blocks. So blocks is the smallest element where you store data, where you retrieve data. Okay, right. So coming back to this picture diagram, how can a table spread or this segment spread across multiple data files? This is very important to understand. If you take a block, Block cannot sit between two data files. It's not possible. What is possible is the extent. You may allocate your first extent from this data file. You may allocate your second extent from the second data file. That is possible. So because both the extents are part of the same segment, you will see that your segment is getting spread across multiple data files. So what's the advantage of having extents spreading across multiple data files? The performance, right? Because the moment you spread it across multiple IO devices, then the performance gain is there. All right. So you can do that. You can explicitly do that, or you can even let it happen automatically as well. So generally speaking, if you only have a single data file, right? If you only have a single data file, then this spreading will not happen obviously. But the moment you have multiple data files, you can have your extents created in multiple physical files. So that means this, since those extents are part of this segment, you may see that the segment is segment data is scattered or spreaded across multiple physical files. That is the understanding, right? So hope that part is clear. So let's move into the next section, which is logical space management. So we discussed about table spaces, physical structures before. We initially discussed about where we can physically store, and then we discussed about the database files and all. And now we are going to come to this section of logical space management. So when it comes to logical space management, when you're creating your, okay, so what is important is a table space. So let's try to understand what a table space is. I told you earlier as well. It's a container, right? It's a logical entity. It's a logical container where you can hold one or more data files. So the table space cannot survive without a data file, right? That means a data file, sorry, table space should have at least one data file. So the table space, uh, so the data file that I'm talking about cannot be shared across multiple table spaces also. So if you create a table space that will have at least one data file, and that file cannot be shared against amongst multiple table spaces as well. One a data file will be only part of a single table space. Now, when you are creating your table space, you have options. What are the options that you have? So the options are you can create locally managed table spaces. You can also have dictionary managed table spaces. So now that we are in the arena of talking about 26 AI and all, we don't really talk about dictionary managed table spaces, right? We talk about locally managed because it's the default as well when you're creating a table space. Okay. Uh, we'll just talk about, okay, still we need to know our fundamentals, right? So that's why we are trying to educate you on these fundamentals. So dictionary managed means, why do we have table spaces? We have table spaces in order to accommodate segments. We saw earlier in the slides, we have tables, indexes, those will get stored inside the table space. Obviously, it is getting stored inside physical files, but at a logical layer, what we will see segments like tables and indexes, right? So when you are having your segments, we also need to talk about extents, right? We need to allocate extents when we want to insert data. All right. We want to store data. We need to have extents because we need docs to store our records. Sometimes we might get rid of our table. Then the extents have to be dropped as well. So this extent allocation, deallocation, right, um, needs to be tracked. So this allocation, deallocation tracking happens at the data dictionary tables. So data dictionary is something that you find inside one table space called system. System table space has quite a lot of data dictionary tables, and it is really there for internal purposes only. We don't go directly access these data dictionary tables. But Oracle has given us some interfaces like what we call the data dictionary views for us to get metadata out of it. Earlier, if you can recall, I queried the $data file. That's a dynamic performance view. I also access DBA data files. That's a data dictionary view. So based on these base tables, we can still retrieve some metadata for our reference. And those will be important to us as well to figure out how many data files that you have in the database. So we use these data dictionary views for that, but still underneath that you have many number of data dictionary tables. And these data dictionary tables will manage the allocation, the deallocations of these extents on these table spaces, right? I mean, on these tables that are there inside table spaces. Just imagine managing such with maybe 1,000 odd tables. It will be a big overhead on the data dictionary tables. Instead of doing that, right, Oracle has come up with a different approach where it basically will ask the table space itself to manage the extents of its dependents. Example, let's say I have a user table space, and you are creating a table called maybe table 1. If the table 1 is getting created inside users table space, the table space users is responsible in tracking the allocated extents, the deallocated extents of that table. So now we are not going to give the burden to the data dictionary tables because it is too much to bear, right? So the tables or the segments that you create within that table space, that particular table space is responsible in managing or in tracking those information about extents. So that is what we call locally managed table space, which is more faster, and it is basically managed through what we call bitmaps, right? So bitmap will basically will have ones and zeros, right? Maybe a particular block, right? If you take in that extent, in an extent, has sufficient space to accommodate new inserts, then maybe it will have a zero value. So that means that block is available for inserts, right? So it could be the other way around, but I'm just taking an example, right? So it could be a situation where maybe you have one for the second block. Second block one means maybe it doesn't have that particular block, doesn't have enough space to accommodate new inserts, right? Talking about space, we have block level parameters also. One such parameter that we commonly use is what we call PCT free. So as an example, let's say we have 20% PCT free value per block, which means a block is entitled for new inserts up to 80% of its capacity. Earlier we discussed, we took an example of 8K block. So you take 80% of it. So up to that amount, you can do new inserts to the table. But the remainder, which is 20%, is only allowed for internal expansions of the block. Let's say I have a record in that block and I'm going to update that. Let's say I was earning, or let's say one person was earning 100,000. I want that to be changed to maybe 1 million or 10 million. So obviously you need more space to hold that data, right? So that data, that expansion will be accommodated within the block because you have a buffer or a space available for internal expansions. So that parameter is called PCT free or percentage free. All right. Okay. So that is basically about the space allocation. So, so similarly, we have the segment space allocation also. So what I basically, talked about was bitmaps managing the blocks, right? They are more into segment-based management because I was talking about a table there, right? So in table, again, it uses something called as bitmaps to figure out whether a particular block is entitled for a new insert or not based on the PCT free value. So if you may ask me, what is the, I mean, whether it is possible for us to change the PCT free value? Yeah, obviously we can change the PCT free value as well, right? So let's talk about implications of changing the PCT free later, but it is possible to do, right? So, so that is the automated part. Then we also have a manual segment space management also, where we use something called as free list. So I hope you can see a small diagram below here, which talks about the free list. Now, free list, right? So you have something called as free list, and we also have something called as free list groups as well. So a collection of free lists will make up a free list group. So a free list is basically a, I mean, if you take free list, it's none other than another block, right? This block basically manages, the space that is available for that segment or for that extent, right? In the segment, the extents are there. So, okay, so as an example, maybe this free list manages, let's say, 10 blocks in one extent. And again, if a particular block reaches that PCT free value, then it will be taken out from the free list because that particular block is not entitled for a new insert. Okay. So similarly, there's another parameter. What is that parameter? It's called PCT used. So let's say I have set a PCT used value for that for that block as 40%. So what happens is that although maybe because of the inserts that you have had on that block, it had actually reached that maybe the PCT free value which we have given 20%, right? So up to 80% you can enter. So maybe it had gone up to that 80%. So now it had come out of the free list. So it doesn't monitor or managed by the free list anymore because it is not entitled to have new inserts. But let's say some records of that block got deleted. You do a delete against the table. So most of the records got deleted. And now the available space got below the PCT use value. Let's say our PCT use value was 40. That was the example which I took. So now the total capacity, available capacity is 60%, right? Which has fallen below that 40%, right? Or maybe not exactly, let's say 60%, 60%, let's say 65% is available, right? So when 65% is there, which is below the PCT used parameter, that block will again be monitored by the free list because now it is again entitled for new inserts. So free list is like a set of linked lists, right? And this is old fashioned, right? So these are managed by blocks, right? Instead of bitmaps managing the blocks. Okay, so the most efficient way is using local manage because it's a default anyways now. But then for 19C, I'm not quite sure. I can't recall, but dictionary manage is getting obsoleted, so we don't need to think too much about it as well. But if it is, if it is manually segment space management, then we use release. But then again, uh, modern versions, we don't use free list as well. We make use of automatic segment space management, which uses bitmaps. Okay. So when you are creating a table space, I'll be able to show you how this is put into action. So what I would do is before talking about the database block, let me stop sharing this one once again and take you to my screen. Okay. Not to my screen, but to my putty window. It's there. Yeah, it's here. So let me just show you how we can create a table space with those properties. Okay. So I create table space. Okay, this time we'll create big file tablespace. What's the difference between a big file tablespace and a small file tablespace? So the one that I created before, oh, I didn't create one, right? I was just keep on adding tablespace data files to a tablespace. But this time I'm creating a tablespace, so I can just say create tablespace, or I can even use the keyword called create big file tablespace. So the difference is that a big file tablespace, as the name implies, can hold only one data file, right? But if I have a small file tablespace just like this, I'm not mentioning anything, just like our users tablespace also, you can have multiple data files added. So there are pros and cons between the two, but not really the time to talk about all of those. But I'm just creating a small file tablespace here, okay? So I can just do big file as well. So let's do big file. So I'll just make it as or name it as big TS, right? And my data file size is 10M. I can go up to max size of 20M. The small files I'm mentioning. Extend management local. Now, what is this? So extend management local, if you can recall, I had two options. One is extend management dictionary, right? Where you let the dictionary tables to track the extent allocation and deallocations of segments that are getting created within this table space called big file TS. But I don't want to do that. I want the table space itself via bitmaps to manage the extent allocation of manage in the sense, to track the extent allocation, deallocations of the segments that I create within this table space, right? So extent management local for me. Then segment space management. So segment space management is the decision between using bitmaps, which is the modern method, or whether you are going to use free list, right? So if I say segment space management manual, then for this table space, I'm going to let the segment spaces be managed via free list. Okay. So, but I will say segment space management auto here. And I can also give uniform size of 1 MB as well. Now, what does this mean? So when I say segment space management auto, right, the segments extend availability of your blocks of free space all managed through bitmaps. And I have given an extent size or uniform extent size of 1 MB. So if my block size is 8K, we can figure out how many blocks that can be accommodated in a single extent. All right. So this is how I create. Let me see whether it is going to work. Oops. Oops. Let me just edit with this option. Edit. Is it max size? To show that I'm right, typing the right syntax. Okay, so data file size. Something wrong with my syntax. Let me just verify that. Data file size. Okay, so for the moment, let me just take this off. I can reinforce it later on also with the interest of some time. Okay, so let me just take that off. This should work. Okay, yeah. So what I've did what I've done here is that I've created a table space for all B. Yes, which are initial size of 10 MB. Let's check this out. Select file name from DBA data files, where file name, sorry, table space name equals big TS. So this is a file that it got created. So if I try to add an additional file, alter table space big TS, add data file size 10M. So this will, sorry about that. So it gives me an error saying that it cannot add additional files to big file table space. So this was not the case that we experienced when we when we add the files to the small file table space. We had 3 files in fact, but the big file table space will only allow one big data file. So if you want to resize it, you can do that. Right? Okay. So, okay. What I wanted to highlight here is that so here we made our table space locally managed. So the extent allocation, deallocation are all managed by the table space uh, using a bitmap. And then for segments also, we gave automatic segment space management, which means a bitmap to manage the blocks availability, right? And then again, based on the PCT free, it can determine whether a block is entitled for new inserts or not, right? And then also I have defined a uniform size that is for my extent. So you can basically calculate how many blocks. So let me just do show parameter db block size. You can see the block size is 8K. So you do select. So we have given 1024 bytes, right? Then 1024 is one name is how much? This is kilobytes. This is 8K, right? So select 1024 kilobytes equals to 1 MB divided by 8. So so in this one extent, so when I say one extent, right? This extent is basically given to segments that you create, because not to the table space, right? So these properties will be inherited by the segments or the tables that we create. Okay. So for example, if I create table. Okay, let me just show you one more thing. Show parameter segment. So you can see here a deferred segment creation is true here, which means that I'm not going to have an extent allocated immediately when a segment is added, because I don't need to allocate or pre-allocate space unless we have data in it. Okay, so let me just quickly do that. We are running out of time as well. So let's do select, create table, test table. There is a number, table space. I want to have it in my big file table space, right? Is that big table? Yes. All right. So describe DBA tables. So these are all data dictionary views that I have, right? I would say describe DBA segments also, and this will be much easier for me. So select extents from DBA extents, sorry, DBA segments, where my segment name. Hope you can remember table is a segment, right? My table name was, okay, the table name was test table, right? So all caps you have to give. Okay, so you can see here there is one extent. Ideally, we should not be seeing this extent because we have made this parameter to defer, right? Segment creation unless, okay, so insert into, because what I wanted to show you was, let me just do this as well. Let's take the extents. There is a initial extent size. Let me take the minimum extents as well from DBA segments, where segment name is stable. Okay, so you can see here that the extent size is KB, it's about 1 MB, right? So this size allocation is right because that is what I wanted to have in this table space. Let me just quickly do one small thing as well. Owner extends, just to verify that we are talking about the same owner. Okay, so you can see it's a sys user. I don't know whether it has any effect on that as well. We can verify that later on. But for normal users, I won't be able to, do it for another user and show you now because of the time. But what I wanted to share you was, so you will be allocating extents. So each extent is 1 MB in size. And we calculated earlier that for 1 MB, you can hold up to 128 blocks, right? So you can have 128 blocks. So you have to fill in those blocks first. And then once that, 128 blocks are full, then only a new extent will be allocated. Okay. So if I do alter table, test table, allocate extent. So what happens here is that if I run this again, you can see that 2 extents have been allocated now. Right. So you can do various other queries as well. You can see the bytes allocated to this segment, so you can figure out how many space in bytes that you have allocated, and you can figure out the extent size or the next extent size as well. Right. So if you take even that here, initial extent is there, and if you query next extent, just query from here quickly. You can see that the next extent size is also 1 MB. Because if you can remember when I was creating my table space rather, I did mention that my table space is having a uniform size. So a uniform size of 1 MB. So therefore, the extents that it will generate will always be 1 MB. Okay, so 1 MB, and then here we have two extents allocated. So yeah, so then each extent can have 8 blocks. Sorry, 128 blocks as we computed. So now 128 into 2, right? So that amount of blocks are available for this particular table to do get your inserts done, right? So since we were talking about blocks, let me quickly stop sharing here and take you back to the slide deck. So the size of the block is determined by the block size. I just showed you the size of the block is 8K for us. And then you can also have non-standard block sizes, which I told you, right? For various reasons, we can have non-standard block sizes. But then again, for SGA, in order to hold, because your default buffer cache will accommodate these 8K blocks. But for the rest, you need to have appropriate spaces allocated in the SGA. We also have something called as row ID. Um, so a row ID basically consists of uh, the object number, the file number, then the block number and the record number. So I will see whether I can show you that one quickly as well. Let me switch myself back to the. So I hope I have. Let me just insert one record. Insert into the table was test table values. So number is all right. I'm just inserting one record. Let's do a commit. So select. So if I do select asterisk from my table, I find that record that I've just inserted. But let's take select first column is A, and we take row ID as well along with that from. So pseudo column means you don't really see it as a column, physical column, but it's attached to this. And then so row ID basically has I think the first 5 characters, 1, 2, 3, 4, 5 indicates the object ID of. So object ID has a unique value, right? In identification. The next 3 will be actually for or is it next 3? Right. So okay, so however, this will have object ID. Then we have the file ID. I think it is first 6, I think. Can check that out as well. And then we have the file ID. Then we have the block ID. So final 3 or 4, 5, can't remember, will basically represent the record number, right? So if you can just check that out also. If I do another insert here with my second record, I put 2 here just to indicate this, and then do a commit. We'll check the row values, sorry, this row ID as well once again. You can see that this has become AB, right? Earlier AA. So this is row number 2. Right? So row ID, I mean, record number 2. So that's why it has gone up by 1. All right. Okay, so that's about the pseudo column. Okay. And then you also can do block compression. So when you say block compression, what happens is that you can see that in a particular block, in the header section of it, it basically keeps, it keeps duplicated. Let's say you have a record, we have 2 records having the name saying Saman, right? So what happens then is that since the word Saman is getting repeated, Oracle will place a small symbol, and it will have the reference. So on the header part of the database block, we'll say, okay, someone will be represented by, let's say, a percentage. So wherever you see percentage, that refers to someone. So this is basically to reduce the storage allocation for these records to make sure that you have many records. So not just someone there, right? So let's say we have another, let's say a date column, which has a similar dates added. So again, another different symbol can be allocated there. And then header will say, okay, if you have, let's say, January 1st, then January 1st will be represented by a question mark, something like that. So you save space to accommodate more blocks, which means we are talking about compression. So when you have compression, if you fetch a single block, the amount of records that you fetch is more than in a conventional block, right? Then we also have something called as pulleys. As pulleys basically is basically, combining, let's say, empty blocks together, merge them together, and then create additional space for for records for you to use. Then we also have something called as row chaining. So row chaining happens when a particular slot is not sufficient to hold a single record. So then the block will go into, a record will span into the second slot or second row of the, we saw in the pseudo columns, row ID, we found the second record coming under in the second row. So, but this particular, record that we are talking about may not be sufficient to be accommodated in one slot. Maybe a large object like what do you call the long columns. Sometimes we have data types called long row columns. So maybe those are not cannot be accommodated in a single record. So it will span across multiple slots, and that is what you call row chaining, which we cannot avoid unless we increase the size of the block. So that is why where we have standard non-standard blocks, we can have bigger block sizes and accommodate such tables having such columns into those, or move them into such non default block sizes, right? So it could be another situation where you have a record here and you are doing an update to that record. Due to this update, the record expands. But since we did not have sufficient space, remember we were talking about free percentage free. So PCT free, let's say it's 20, but that 20 is also now occupied because due to internal expansions. So when another expansion happens, since the record cannot be accommodated in one one block, so the record has to be migrated from this block to probably to a adjacent block. And that situation is what we call a migration. So row migration is costly. Why? Because you look for the record and you come and check the record here, but you don't find that record. So you have to do another IU in order to go and fetch it from the relevant block, which creates more IOPS, right? In order to reach up to your record, and migration therefore is costly. So if you have, you can verify in the database whether you have migrated rows and do certain operations to, maybe we can do some defragmentation there and then get them in order, but something that you have to look into. We also have something called as high watermark. So high watermark has low high watermark and normal high watermark, which you can see in this diagram as well. So what happens here is that when you have data stored, according to this diagram, the dark or the shaded ones, they have data populated. So it could be a situation where you have already formatted these blocks and added records, or it could be a situation where you already had data, but you have deleted few records or deleted records from these blocks. They are empty, but the low high watermark won't change. So what happens is that when you access the table and if you do a full table scan, in other words, if you access the entire table, the search will start from the starting point, obviously, and it will go until the last block where you have the high watermark. So when you have fragmentation in your tables, where you have high watermark or low high watermark placed somewhere here, but you only have data maybe up to about the first three blocks. Still, the search will carry on until the low high watermark, right? Which is going to take more time, right? Although we don't have data, it will go up to the high watermark. So we also have a generic high watermark as well, which means this place you have not formatted these blocks. The extent is allocated, but the blocks are never been used. So search cannot happen up to this point. But when the high water mark, the low high water mark increases, accordingly the normal high water mark will also move, right? But then the good part is that this is never been used, right? So therefore there will be no impact on the performance in that sense. So the moment you have more changes done to your tables and they are fragmented, then you can reduce this high water mark up to the point where you only have data by using certain mechanisms. So if you have heard of doing rebuilding, doing maybe truncation of your tables, or we also do we do something called as shrink. So all these operations will help you in bringing down this low high watermark to the point where you really have data. All right. So that way, again, your query performance will go up because the query need not to access the whole set of tables where you really don't have data. All right. Okay. So that brings us probably to the end of my slide presentation today. I'm sorry for taking a bit more time. So, okay. So we're ready for questions if you all have any. So I think last time we had a few questions asked. So feel free to ask any question that you have on this section or maybe any other section as well that we have completed
Yeah.
before.
Mr. Gayan, I have one question. So you mentioned that if a segment is not no, if a block is not no, never used or no, if a block does not have any data, it it still will search and will generate some high watermark.
Yeah.
High watermark.
So,
Is
mm.
that does that mean it will generate high watermark contentions or HW? Is it same with HW contentions?
Okay, so when I say high watermark, it's actually, let me just take that slide out as well. Just right. So we take the point also out. Okay. So when I say high watermark, so these are not something that we have set, but let's say for the first time when we do an insert, just take an example. Okay. So we have inserted the records throughout all these blocks. Now they are filled with blocks, records. Okay. So the last point where the data is inserted is what we call the low high watermark. Okay. So what happens here is that then when you search data, I'm not saying that all the time it will reach up to the low high watermark because I mean you may have an index created and only you want to select a few records only, right? So if you have an index will determine what are the blocks to be accessed. Then it will direct you to the right blocks to access. So you don't need to do a full table scan. But in a scenario where you access the table in full, meaning you need all the data, then it will start from here and it will read up to the low high water mark. What happens is that even though you have done some deletions mm, right? And then you have got rid of some records in all maybe all the last three blocks. Still, the high water mark will not change. So since it is not changing there, right? But then maybe the last three blocks are empty, but you had data before, right? So if you do a full table scan, again, it will go up to the low high water mark. But then if you want to do inserts, inserts can take place in these blocks also because they are empty. It doesn't need space from unformatted areas, right? Then, so that's how the high watermark works. So so what happens is that when you have high watermark, the time spent, even though you don't have data at all, will be more or less like as if you are accessing the full table having data. Okay, so that's basically about low high watermark. About the contention, now what happens is that when let's say people or when two or more people try to do inserts to the same segment, right? Obviously, what happens is let's say that you have already filled in all these blocks, and you are allocating a new block, right? So maybe two people or two sessions are trying to push the high watermark, right? Push the high watermark. So because why? Because I mean it has to be pushed because you are inserting into new blocks, right? So when two people or more people wants to do this, right? So there will be a contention in order to access this high watermark resource.
Yeah.
So that is where the contention happens when many people or concurrently wants to push the high watermark from its original location. So that is where the contention comes. But generally, when you're accessing, when you're doing a select or anything, there's no contention on the high watermark. Just that it will reach up to the high watermark when reading, when you're doing a full table scan.
Yeah. Okay. Thank you, Mr. Guy.
Yeah, no problem. So anything else that you all want to know? Okay, so Kandu,
Yeah.
good to
Thank you,
close.
Mr. Guy, for joining for your time as well.
Yeah,
Yeah, I think that's it probably for today. I'll share the upload the this video for YouTube and share it in the group. Yeah.
yeah, sure. Thank you so much. Have a good night.
Yeah. Thank you, Mr. Guy. Okay. Thank you
Thank you.
everyone for
Good.
joining.
Thank you. Good night.
Yeah. Good night.